Okay, so continue on our discussion for Unit 6, timers of the MB90F387S. So the last topic we're going to cover is the PPG timer. The, uh, the PPG timer, or PPG, otherwise known as the pulse pattern generator, is actually a module in the Fujitsu MB90F387S that could generate a pulse pattern, and it has an 8 or 16-bit resolution option. So basically, the PPG timer is a reload timer module, which we discussed earlier, which has two channels, PPG0 and PPG1, that it outputs a pulse in any frequency and at any duty cycle that we would like to to have that pulse. Basically, PPG timer uh, is also could modulate a pulse. So meaning when we say modulate, we can change the duty cycle beyond 50% or less than 50%. So a combination of these two channels, PPG0 and PPG1, you could have an 8-bit PPG output, which two-channel independent operation mode, 16-bit PPG output mode, and 8 plus 8-bit PPG output mode. So these are the three modes we could operate from. So if you want to use the entire 16-bit resolution, then therefore we could only you're limited only to two channels, while the 8-bit mode we could use also an 8-bit two-channel mode, but if you want to maximize the four channels, then we can use the 8 plus 8-bit PPG output mode. So the functions of the 8-bit, 16-bit PPG timer consist of four. So we have 8-bit reload registers. So if you notice, if you still remember our discussion in about reload timer, so we have this reload timer or reload register. This time it's that was 16-bit. This time we have 8-bit reload timers. We have four. So we have PRLH0 to PRLH PRLH1. Actually, these are just the this represents the high byte and the low byte, which basically consists of a 16-bit timer. So PRLL0 is the lower byte for PRLH0, so as PRLH1 is the high byte and the PRLL1 is the lower byte. And there are two PPG countdown down counters since it's a reload. So we have PCNT0 and PCNT1. Now these individual settings of high and low widths in output pulse enables an output pulse of any cycle and duty ratio. So here we can set the duty cycle to not to beyond 50% or below 50%. The count clock can be selected from 6 internal clocks. So we have a choice of count clocks, and the 8-bit, 16-bit timer can be used also as an interval timer by generating an interrupt request at each interval time. So if you want to use the PPG timer as an interval timer, we could do it by enabling the interrupts, so that at each interval there is an interrupt request. So we can then calculate the time of each interval, and then we could use that to any application. An external circuit also enables the 8-bit, 16-bit PPG timer to be used as a digital to analog converter. So Um, as we introduce, or as I introduce you to the Fujitsu MB90F387S, one of its most familiar peripherals is the AD converter. So this time, by using the PPG timers, we can also do the inverse of the AD converter by using it as a DA converter. So here are the channels of the PPG and the pins of the PPG timer. So as you notice that we have basically two modules here. So we have PPG01 and PPG023. So PPG01 is connected to two PPG output pins, as well as the PPG23. Now remember that these four output pins are also high current outputs. Therefore, we can basically drive a motor or any device that requires a higher current. So the module PPG01 controls pins PPG0 and PPG1, while PPG23 controls the output pins PPG2 and PPG3. So this is the block diagram of the reload timer. So since we have two 16-bit reload timers, so this is the timer 0. So basically, the timer 1 is the same block diagram, although it might have a different register name. So there, the indication here is of course the suffix instead of 0, it's now 1. So here is the reload 8-bit reload counters, PRLH0 and PRL0, and this is the reload register, high and low selector. This is now our PPG0 down counter, and this is now PCNT 0. Okay, this is 16-bit, and over here this is the control register. That's the PPG operation mode control register, and this is the count clock selector. Okay, so we can select to the different clock sources for our PPG timer. So we have the 512 over H clock, and one over machine clock, 2 over machine clock, and so on and so forth. So this is controlled by the selection of the count clock is controlled by this register here, PPG01, or the count clock select registers. For the details of the bits here, refer to of course, the hardware manual. So we have the output, the PPG output control. This is PPG0. Okay, so we have also an interrupt request output, and obviously the interrupt is controlled or is going to be configured by the PPG or the register PPG C0. So the registers that we have to just remember is the PPG01 as a count clock select register, PPG C0 for the PPG0 operation mode control, and two reload registers, the 8-bit reload registers representing the high and the lower bits. So basically, a clock pulse is normally has a period, of course, and for a 50% duty cycle, it means that 50% of the period the clock signal is high, and 50% of the period also it's low. Therefore, for a 50% duty cycle, so the period is calculated as T off plus T on, or basically T off is equal to T on. If we are going to modify the duty cycle or modulate duty cycle. So we can now have the same period here, but we have now a different value for T off and T on. So in this case, T on is just 25% of the period. So therefore, we call the duty cycle at 25% because it's 0.25 times the period. So that gives us that time where the signal is high. So it's basically less than 50%. So if you notice also the T off is much longer than T on. So therefore, the pulse has been modulated in this case. Now we could also do, we could also have T off would be lesser than T on. Okay, so if T on is not equal to T off, it means that the pulse has been modulated and it's not operating at a 50% duty cycle. Now to illustrate further, the count clock cycle register for the PPG01 and PPG23. So it actually counts. The period of the signal, okay, while the two reload counters counts the high and the lower, the high and the low signals of our pulse. In this case, so we have here PRLLX and PRLHX. X here stands for the it's either 1 or 2. We'll be using timer 0 or timer 1, okay, or PPG 0 or PPG 1. So this if we refer this to the previous slide, therefore PRLL represents T off, and PRLH represents T on. Okay, and this is the assumption that PPG01 and PPG23 are operating as 16-bit PPG channels. So what does this 8-bit, 16-bit means? Basically, the resolution of our count clock cycle register. For example, if we are going to use the 16-bit, so therefore, we are going to use the two 8-bit modules. So combine them together, so therefore we come up with a much more higher count, and it turns out in turns you have this a much more finer steps in the count from the beginning of the cycle to the end of the cycle. So if we are going to be using 8 bits, so therefore the counts in between the here and here is just 256. If we are going to use the 16-bit timer, so we have a count of about 65,000, so from the start to the end of the cycle. So therefore, the 16-bit timer is much more, does have a higher resolution. And what does the higher resolution does is that the higher resolution provides a much more precise adjustment of the duty cycle. Okay, so if you want to adjust the duty cycle either more than 50% or less than 50%, so you can have lesser the finer steps allows you to have a precision adjustment compared to a lower resolution that is 8-bit. So an example here is that we are going to use the piezoelectric buzzer to connect it at P17 on basically at PPG3, so the third PPG pin. So we're going to apply a 2 kHz signal at 60% duty cycle. Now please refer to the Fujitsu starter kit manual for the schematics where this piezoelectric buzzer connected. Well, it's connected as we can see here. It's connected at P17 with also the alternate function of P17 being as the PPG output, 100 PPG output pins. So before we start, we have to solve the value for the PPG reload register. So say for example our count clock frequency is about 2 megahertz and the desired output frequency is 2 kilohertz. So this is now the output of PPG3. It's about 2 kilohertz. Okay, so therefore we are going to calculate the clock factor at 2 times 10 to the power of 6. That's the 2 megahertz. So we divide that with 2 kilohertz, our desired output frequency. So we basically just divide the clocks here. So which means that we will divide. Okay, we will divide the output, the clock PPG count clock frequency by the desired output frequency to come up with this factor here. This factor 1000 is the number of counts at 100% duty cycles. It means the entire period of the pulse, so we have 1000 counts. Okay? Now obviously, since it's 1000 counts, to achieve a frequency, an output frequency of 2 kilohertz, therefore we are not going to be using an 8-bit resolution here because the count is more than 256. So therefore, we are going to use the 16-bit timer in this case, so that we can achieve a we can achieve the desired output frequency. So the period then, since this is the number of counts at 100%, so we can now calculate the number of counts for T on and T off. In this case, T on is 60% of 100%, therefore we have 600, while T off obviously should be equal to 400. So therefore the values for PRLH3 and PRLL3 is basically 600 and 400 respectively. Assuming that all of this is assuming that we have FOSC being 4 megahertz, and of course we're going to be using the one over machine clock, so a 2 over machine clock, so therefore we have the PPG count clock frequency of about 2 megahertz. Okay, now this is a sample code. We'll be using the PPG 23 channel. Okay, so we set P17 as an output, and we're going to use the register PPG-C23 because the PPG3 belongs to the PPG23 channel. So we have to enable that by setting bit PE1 to 1 to enable the PPG pin output, and also we are going to use the PPG23. So this is now the selection, the clock selection. So we are now going to select the clock as being the count clock setting, same as CPU. Now the CPU has CPU is basically driven by a clock of about 2 over H clock. So therefore, if our oscillator is 4 megahertz, therefore we are going to be operating the same as CPU at about 2 megahertz. Now, we will now set the reload values, the reload register values, PRLL3 for the lower byte, that's 400, and 600 for PRLH3, that's the high byte, so that we can achieve a clock factor. So basically we just have to add PRLL and PRLH, and then it should be equal to the clock factor. So varying the value of these two, that's basically modulating the pulse. If we have 500 for both, then we have a 50% duty cycle. So the last statement here is now to enable the timer. So before we enable the timer, so we have to set up everything. So that's why we have to do it last. So that's now to enable the timer. So that's bit PEN1. at PPGC23. Now, remember, PPGC23 is different from PPG23. PPG23 is the register that allows you to select the count clock for our timer. Okay, so if you have questions about the PPG timer, so basically what it does up to this point is that it will just generate the clock or the desired clock frequency, that's 2 kilohertz, and of course the duty cycle, that's around 60%. So we have an output clock of 2 kilohertz at 60% duty cycle. So this would vibrate. Okay, this would vibrate the piezoelectric buzzer, and basically creates sound. Okay, now adjusting the duty cycle also adjusts the does not change the frequency, but otherwise adjust the amplitude or the magnitude of the sound. So if you are going to go for, let's say for example, so 100 or 90%, of course the sound would be much louder than the sound produced below 50%. Now, we've discussed duty cycle in the PPG timer and how we can modulate the duty cycle, and we do this by basically in the concept of pulse width modulation. So if we modulate the pulse, we call it pulse width modulation, or PWM. Now it turns out that the duty cycle and the voltage are actually there is a direct relationship between these two. It turns out that the voltage output of the signal is directly proportional to the duty cycle. So increasing the duty cycle also increases the voltage output. So for example, at 99.9% duty cycle, the signal is on at all time, and the voltage output will be V maximum. So for example, if your V maximum is 5 volts, therefore at 99.9 or technically 100%, so the output now is 5 volts DC. So you can no longer see a pulse there, so you can also see just a direct current at the voltage, the maximum voltage. In theory, if the pulse is 50%, so therefore the theoretical or the voltage output should be 50% of Vmax. If Vmax is 5 volts, therefore the output voltage is only 2.5 volts. So if you are generating a pulse at 50%, therefore you are not generating the maximum voltage. Now, increasing the duty cycle also increases the voltage output. So for in this case, we can now vary the voltage output by just varying the duty cycle. So this is now, here's the graph representing the speed and the duty cycle, the relationship of the duty cycles. As you can see, so we have here a linear correlation between the duty cycle and the speed of the motor. Now we know that we can control the speed of the motor by varying the voltage supply of the motor. So if we're going to feed a 5 volt DC motor with 5 volts, therefore the motor is operating at its maximum RPM, that it's designed for a 5 volt source. That is why if we have a 5 volt DC motor and you put a 12 volt supply, it would burn out. Basically, it would burn out the motor. If we do apply a certain voltage that's over the rated voltage of the motor. So the modulating the pulse gives us the ability to digitally control DC motor. So here is a concept conceptual framework of how we can control DC motors. Basically, we just turn on, off the supply of the DC motor. So basically, we're just turning it on for a certain period of time and turning it off for a certain period of time. We do this at a regular interval, so we can rotate the DC motor at the speed that we want. So by modulating the pulse, so we can now vary the DC motor to turn it, to have it run faster or slower in a digital manner. So, but before we can do that, we should have a PWM driver in between the voltage out of the pulse and the DC motor, because sometimes the voltage output of the microcontroller or the pulse wave generator is not enough to drive the motor. But in this case, since the MB90F387S, the PPG output pins is high current, so theoretically it could drive a DC motor, a 5 volt, at least a 5 volt DC motor. Okay, as I've said that we can use PWM to control the speed of DC motor, but we have to be very careful as well in also selecting the DC motor, and if the pulse width or the pulse could not drive a DC motor, then therefore we need to have special drivers that can support switching, a very high frequency switching of signals, on and off signals, so that the voltage could also vary. So that wraps up our discussion about the PPG timer and the application also of the PPG timer. Not only that it generates a pulse, but we can also modulate the duty cycle, and it's perfect for controlling the speed of a DC motor because of the relationship between the duty cycle and the voltage output. So if you have questions about our video lecture today, so please post your question in the discussion board in our website. So that's it. I see you guys on regular classes. Thank you, and have a good day.